do. Welcome to Dosing and Renal Impairment Part 5. Hooray! We're getting toward the end. I don't know how to get rid of this. If someone could tell me, I'd appreciate it. Okay, we're going to be talking about reabsorption, which is the final step of renal clearance. Remember, we have glomerulus, the blood comes through here, and then comes into the nephron. This is the nephron. And it gets filtered here. Only the free drug gets through here. And then in the proximal tubule, we have secretion, which is dependent upon these acid and base secretion sites that drugs and other things will be competing for to go into the urine here. Against a concentration gradient, so it's an active process that can be saturated. As you're moving through here, remember we're reabsorbing water like crazy, right? Because we don't want to have to drink all the time in order to be able to maintain our fluid status. So this is getting more and more concentrated as we move down here. The drugs and everything else in here is getting more and more concentrating as we reabsorb water like crazy. When we finally get down to the distal tubule, we start to see reabsorption. So we're reabsorbing drug from the urine back into the blood. So this is working against what we're actually trying to do, which is get rid of the drug, right? Reabsorption is usually a passive process, which means it does not require energy, because remember, this is much more concentrated and this is less concentrated. So the drug is going to naturally want to equilibrate that across this membrane. Now, in order for drug to move across that membrane, there has to be a concentration gradient, first of all. Otherwise, you're going to need energy to move against it, and this is a passive process, does not need energy. So first you need a concentration gradient. Then in order for it to move through there, remember it has to be unionized, and it also has to be lipophilic enough, lipid-loving enough to move through that lipid layer. So there has to be a concentration gradient, it has to be unionized, and it has to be lipophilic enough. Remember, ionization character is determined by Henderson-Hasselbalch. So we need to have, for acids, I just remember that they're, remember a little trick, that they're not very polite. So they put I over U. So ionized over unionized species. So if the pH goes up, more alkaline, it's going to favor the numerator, which is ionized. If the pH goes down, it's going to favor the unionized species. If we have that alkaline situation, again where the pH goes up, it favors the ionized, which means it can't easily go across. It's going to get stopped there, isn't it? So it can't easily cross that lipid layer. So this is going to, an acid in an alkaline environment is going to decrease reabsorption, which will increase renal clearance, which will then decrease our CSS average. So you can see how these drug interactions work. If you acidify the urine, then it's going to favor what's in the denominator, which is unionized, which is what the drug has to be to reabsorb. So that's going to increase reabsorption, which will decrease renal clearance, and therefore wait a minute, that's wrong. If you decrease renal clearance and increase CSS average. No, this is correct. And also it will change half-life too, right? So it will increase half-life. This will decrease half-life if everything else stays the same, right? Bases are the opposite. Bases put unionized over ionized. So in an alkaline environment, it's going to be more unionized, therefore favoring reabsorption, and you're going to be in this situation. If it's in a more acid environment, it's going to be more ionized, and therefore it's going to have a decrease in reabsorption, increase in clearance, blah, 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 blah. So you need to be able to follow all this through. How do you find a change in concentration gradient? Well, when we give osmotic diuretics, what that does is slows down the reabsorption here. So what does this do? There's not as much of a concentration gradient. Therefore, if you destroy this concentration gradient, not as much is going to get reabsorbed. So you would have a decrease in reabsorption, increase in clearance, decrease in CSS average, and decrease in half-life. Lipophilicity is probably not going to change at all. It's a property of the drug, and that we look at the octanol to water ratio, and that gives us an idea of it's more lipid loving or more water loving. Okay, so that's reabsorption. So now to put it all together, what we do is we look at, to try to figure out drug and disease interactions, we try to figure out, is the predominant process reabsorption or is the predominant process secretion? How do we do that? Remember, we look at the E ratio, which is really just looking at the relationship between renal clearance and filtration clearance. So if more is cleared in the kidneys than what was filtered, then we know that, so if the E ratio is greater than 1, drug must have been added, so that's secretion. If its E ratio is less than 1, that means more was filtered than was gotten rid of in the kidneys, therefore it has to be, reabsorption has to be the winner. So how do we figure that out? Well, your patient is taking digoxin. His total clearance, total body clearance, is 190 milliliters per minute. You know from the literature that 68 micrograms of a 100 microgram dose is recovered unchanged. That means it has not been metabolized. Therefore, this is our FE, isn't it? I don't think I need a calculator to figure out our FE is 0.68. So to determine our renal clearance, we would just need to multiply this times 0.68, because that would give us our renal clearance, total body clearance times FE. And let's see, I worked this out. So what did I get? 129.2. And the units on that will be mils per minute. So that's our renal clearance. That's how much makes it out of the body in mils per minute. Now I wish I knew how to erase this, but I guess that doesn't do it. Okay. So I think I can add a blank slide. Maybe I can't. Anyway, so now we'll do filtration clearance, which is GFR, which we know is about 125 mils per minute in a normal patient, times the fraction that's unbound, because the fraction that's unbound is the amount that would be able to make it through that filter. So was that given to us? We could look it up if it wasn't. We also know that digoxin is 25% bound, so our fraction unbound would be 0.75, wouldn't it? So again, just plug and chug that. And I got 93.75 mils per minute. So we have at the filtration site, we have a filtration clearance of about 94 mils per minute. And then after it goes through the whole thing, what's going out in the kidneys, out in the bladder, out in the urine, is 129 milliliters per minute. So more is going out than was filtered. So what has to be happening? There's got to be predominant secretion. So the predominant process is secretion. So we would have to know, is this an acid or base? And I would be mostly looking for other acids or bases with lower KTSs being added or removed that would compete with our digoxin for those, in this case it is an acid secretion sites. So that's how we use this information. Okay, that's all for now. I'll see you in part 6. Thank you. Bye-bye.